Hello, DP students. Starting from this unit, we will study calculus. What is calculus? Calculus involves three important parts. As the first step, of course, calculus will be more complex than what we were talking about here. But anyways, the beginning steps for calculus involve limits, differentiation, integration. Calculus is a Latin word meaning purple because ancient Romans used stones for counting. The first stepping stone for calculus is called limits. In mathematics, the limit means when x is approaching a value, what value does y approach? Based on limits, our early mathematicians, especially Leibniz and Newton, they developed a differentiation. What is a differentiation? Differentiation just looks like the purple. So if you have the curve of a function, this time I don't look at the whole graph of that function. I look at the point. There are infinitely many points on the entire curve of a function, right? So we look at each individual point. So that means we change the whole to the point or piece view to look at what can happen right beside this kind of point or on this point. What will happen to that point? Okay, what will happen to that point? By looking at what will happen to every single point on the curve, we can get the view on the entire curve. Integration is the inverse process of differentiation. Integration means we go backwards in differentiation. This time, I put all the pieces together back to form a whole. So, if you want to know calculus better, please also watch two attached videos to this lesson. Right now, let's look at the first part of calculus, limits. What is a limit? We do have an informal definition and a formal definition for limits. However, at this moment, if we introduce the formal definition for a limit, it may be quite abstract to you. In order to lead you into calculus, we will introduce the informal definition of a limit. Each of students will be introduced to the formal definition of a limit in the optional calculus. Let's look at the informal definition of a limit. Think about a function, f of x. This f of x can be made as close as we like to some real number, a, by making x sufficiently close, but not equal to a. So what does that one mean? So when x is getting closer infinitely, but not equal to a value a, then we look at how does the y value approach and which value can y approach. So we say that f of x has a limit of a. When x approaches a, the y value is approaching the capital letter A. Even this informal definition probably still sounds abstract to you. We will give you some examples to help you understand the meaning of limit better later on. If you do have limit f of x, when x approaches a, this y value is approaching capital letter A. We also can say this function is to converge to a. X approaches a, meaning x does not reach a. The x value doesn't have to be equal to a. It's just approaching a. Then the y value is approaching also a value. This value is called the limit. Why is it important for us to know and understand the limit? The limit can help us examine the behavior of the function at a point or around the point. If we can examine the behaviors of the function around any point, or we can see all points on the curve, on the graph, we can get the idea or get to the view about its graph. Right now, let's look at an example. F of x is equal to 5x plus x squared over x. This is a rational function. Hope that you guys all know that. This function is not defined when x equals 0. So if you want this function defined, x cannot be 0 because the denominator cannot be 0. However, we still can look for its limit of y when x is approaching 0. Even though x cannot be equal to 0, I still can examine the behavior around x equals 0. Let's graph this rational function. So if you want to graph it, I think we can simplify it first. There is a GCF in the numerator. Let's take it out. And this GCF in the numerator can be cancelled out with the denominator. We only have 5 plus x left. Of course, the simplified function also has the same restriction for x as its domain. So x cannot be 0 for this function. And look at this function. This function is a linear function. We can graph this one even without using a calculator. Of course, you still can use a graphing calculator to graph this entire rational function. But the graph will be the same as this one. However, since this linear function has a restriction in its domain, x cannot be 0. That means on the straight line, I need to put an open circle 0, 5 on this linear function graph. Why this point cannot be defined? X cannot be defined for this rational function, and this simplified function is equivalent to this one. Therefore, this one doesn't have x equals 0 either. But we still can examine the behavior of the graph around this point. When x is approaching 0, you can see the y is approaching 5. X also can approach 0 on the other side. And the y value you look at here is also approaching 5, even though y cannot be equal to 5. Remember, the graph of this rational function is a straight line with this point missing. And this is also a very good example for a discontinuity. And discontinuity is called a point of discontinuity. In limits, we do have 3 different types of the discontinuity. The first type is a point of discontinuity, which also can be called removable discontinuity, just like this one. In PC12, we also call this open circle a hole. The second type of the discontinuity is jump discontinuity. And the last type of the discontinuity is called infinite discontinuity. We will introduce all those different types of the discontinuity in the following example in section 2. Section 2, visualizing limits. Let's consider we do have such a function which involves those kind of, pieces in its graph. And this is a function, of course. You guys can see that the graph passes through the vertical line test. Let's look at, on this graph, what is f of 2? What is the meaning of f of 2? F of 2 means I'm looking for the y value when x equals 2. So when x equals 2, its corresponding y value for this function is 3. The second one, you do have the notation of limit. So this one means I'm looking for how and what value y can approach when x is approaching 2. And there is a negative sign on the right top of 2. This negative sign means x is approaching 2 from the left hand side. So let's look at the graph when x is approaching 2 from the left hand side. The y value is approaching, so you look at the graph from, right, when x is approaching 2 from the left hand side. So the y value is approaching 3. From these two questions, you probably can know the difference between these two representations. The first means a function notation. This is the y value when x equals 2. When you have the limit with f of x, so you're looking for the behavior around x equals 2. When you look at the behavior around x equals 2, you can look at this point from the left hand side or the right hand side. So this one means I'm looking for what y value will approach from the left hand side when x is approaching 2. Let's look at number 3. Limit f of x when x is approaching 2 positive. This 2 plus means x approaches 2 from the right hand side. It's called a right hand limit. So this one is called a left hand limit. So when you want to find the limit, you always need to put down the limit notation. Otherwise, it just becomes a function notation. Okay, note the difference between a limit and a function value. So let's find the right hand limit. So this time, your x is approaching 2 from the right hand side. This is from the right side. So look at the y value on the graph. So you look at the graph from the right hand side. When x is approaching 2, you will find that the y value is also approaching 3 from the right hand side. So if your left hand limit is equal to the right hand limit, we can even say the limit of this function exists when x approaches 2. When x approaches 2 from the left hand side, y is approaching 3. When x is approaching 2 from the right hand side, the y value is also approaching 3. That means when x approaches 2, no matter which side you have, this y value is approaching 3. Let's look at question number 5, f of 4. Let's go back to the graph. We need to find the y value when x equals 4. So x equals 4, the corresponding y value shows a hole. This hole means this is a point of discontinuity. So that means the graph discontinues here with this open circle, open dot. So f of 4 is undefined. There's no y value for this open circle, for this point of discontinuity. But does this point of discontinuity affect the limit value around 4? Let's look at 6. What is the limit value of y when x is approaching 4 from the left hand side? So x is approaching 4 from the left hand side. Even though this is a hole, we can see the y value is approaching the y value of this hole, which is 6. What is the right hand limit? So when x is approaching 4 from the right hand side, you look at the graph from the right hand side. So the y value on the graph is also approaching the 6. The left-hand limit is equal to the right-hand limit. Therefore, the limit of this function when x approaches 4 exists, and the value is 6. The limit exists because the left-hand limit equals the right-hand limit. Means limit f of x, x approaching 4 negative, equals limit f of x, x approach 4 positive. So the point of discontinuity doesn't affect the existence of the limit. At a point of discontinuity, your limit still could exist at this point. Let's look at f of negative 3. F of negative 3 is here. This open dot means this y value is undefined. F of negative 3 is defined at this point. The corresponding y value is 1. Let's look at the limit value from the left-hand side and the right-hand side of this x equals negative 3. Limit x is approaching negative 3 from the left-hand side, the y value, so you look at the graph, you need to make sure the x value is approaching negative 3 on the left-hand side. So you need to look at the graph on the left-hand side of x equals negative 3. So the y value is approaching 3. The right-hand side limit value. When x is approaching negative 3 from the right-hand side, the graph should be this one. So the y value is approaching 1. The left-hand limit is not equal to the right-hand limit. Therefore, limit f of x when x approaches negative 3 is called does not exist. D and E is the acronym of does not exist. The limit does not exist because the left-hand limit is not equal to the right-hand limit. Namely, limit x approach negative 3 negative f of x is not equal to limit x approach negative 3 positive f of x. At x equals negative 3, we can see the function, the graph discontinues at this x equals negative 3. So the left part, the right part, they gotta split it up. So this type of the discontinuity is called a jump discontinuity. There is a gap between the left piece and the right piece. So let's continue to look at question number 13. What is the limit value when x is approaching negative 7? So you need to know, right now this time we don't show you the left-hand limit and the right-hand limit. However, you need to ask yourself, what is the left-hand limit? What is the right-hand limit? This limit exists if and only if the left-hand limit is equal to the right-hand limit. If these two limits are not equal, this limit when x approaches negative 7 does not exist. So let's look at what is the left-hand limit when x approaches negative 7. From the left-hand side, so the y value is approaching 1. How about the right-hand limit when x is approaching negative 7? Look at when x approaches negative 7 from the right-hand side. We look at the graph. From the right-hand side, the y value is also approaching 1. Therefore, the left-hand limit equals the right-hand limit. When x approaches negative 7, y approaches 1. Right now, let's look at what f of negative 7 is. X equals negative 7. On this piece, you will see there is a hole. However, x equals negative 7 is defined here rather than here. So when x equals negative 7, this point shows the y value, which is negative 2. So we do have the limit exist at x equals negative 7. However, this piece can have x equals negative 7 undefined and you define x equals negative 7 in a separate point. And with x equals negative 7, you will find the vertical line still can pass at x equals negative 7. Right? The vertical line still will intersect the graph at one point, which is just here. Okay. So right now let's move to 15, 16, 17. When x is approaching 6 from the left-hand side, what does y value approach? Let's look at x equals negative 6. Oh, it's here. But with negative 6, we look at the graph. On the left side, the graph is getting closer to x equals negative 6, but never cross over or touch this line. On the right side, you look at this part, it's the same. The graph can go up forever, infinitely, but never cross over or touch this line. And we have already learned this line in chapter 2, and this line is called a vertical asymptote. So this function has a vertical asymptote at x equals negative 6. When x is approaching negative 6 from the left-hand side, this function y is approaching positive infinity. When x is approaching negative 6 from the right-hand side, the y value is also approaching positive infinity. These two limits are the same. The left-hand limit is equal to the right-hand limit. Therefore, when x is approaching negative 6, the y value is approaching positive infinity. Some of the students probably will think, is there any difference between positive infinity and the d and e? Can we put down d and e here? You can put on d and e as the limit value here. However, we want to be a little bit more specific. I do agree, each limit does not exist. However, we also want to show the y is approaching positive infinity to demonstrate the behavior of this part of the graph. So please feel free to use positive infinity or negative infinity to show the limit value of a function when x is approaching a constant, even though they don't really exist. And those three limits also can show me a very important mathematical definition for the vertical asymptote. We can look at it here. A vertical asymptote occurs when x is approaching a constant. Your y value can approach positive infinity or negative infinity. C is a finite, means C is a finite constant. This is the mathematical definition for vertical asymptote. At x equals negative 6, this also shows me an example of the third type of discontinuity. At x equals negative 6, both of the pieces can go up forever, infinitely, close to this x equals 6, but never touch this line. And this line is the vertical asymptote. But look at these two pieces. They don't join up. They discontinue. So x equals negative 6 is the infinite discontinuity. The reason we call infinite, it's mainly because look at the graph on the left side, it goes to positive infinity. On the other side, it goes to positive infinity as well. Let's look at another infinite discontinuity in this graph. It happens when x is approaching 0. When x is approaching 0 from the left-hand side, we can see the y goes down infinitely. So this limit value is going to negative infinity. On the other side, when x is approaching 0 from the right-hand side, the y value, you look at this piece of the graph, the y value is going up forever. The y is approaching positive infinity. How about the limit when x is approaching 0? X approaches 0, the left-hand limit is not equal to the right-hand limit. For this case, you have to put down d and e for the limit value when x approaches 0. because your left hand limit is not equal to the right hand limit. However, x equals 0 is still the infinite discontinuity. Anyways, you will see negative infinity for the limit value or positive infinity for the limit value when x approaches 0 from the left hand side and the right hand side respectively. Right now, let's look at the end behaviors of a graph. What is the end behavior of a graph? So, look at the graph. The left end. Left end means when the x is going to the negative infinity. So, when x approaches negative infinity, what does y value approach? Look at the graph. I'm not so sure if you guys can note there is a horizontal asymptote. Therefore, the y value is approaching -3 when x approaches negative infinity. This is the left-hand behavior. The graph also should have a right-hand behavior, which is here, when x approaches positive infinity. So when x approaches positive infinity, look at the y value. This arrow shows the graph keep going down forever. So the y value is approaching negative infinity. A horizontal asymptote occurs when x is approaching infinity, can be positive infinity or negative infinity. The y value approaches a constant, a finite constant. Therefore, y equals b is a horizontal asymptote. And this is the mathematical definition for the horizontal asymptote. The horizontal asymptote doesn't have to occur to both of the ends. It can just happen to one end. In this case, the horizontal asymptote only exists for the left-hand side. There's no horizontal asymptote on the right end behavior. No asymptote on the right end, since we have x approaches positive infinity and the limit value also approaches negative infinity here. So two infinities means there's no horizontal asymptote. And the asymptote can be vertical or horizontal asymptote. Only occurs if there is a single infinity, not for double infinities, for both of x and y. Question number 21 and 22 also show you guys the end behaviors. End behaviors are the trends of the graph when x approaches positive infinity and a negative infinity respectively. I used the above example to show you guys three different types of the discontinuity. Any discontinuity means the graph is broken at this x value. What is the definition for a continuous function at a point then? Let's look at this definition. A function f is said to be continuous at x equals a if and only if three conditions are all satisfied. The first condition is f of a is defined. Limit f of x when x approaches a exists. That means the left-hand limit when x approaches a negative. This limit is equal to the right-hand limit. Limit f of x when x approaches a positive. F of a is also equals the limit value when x approaches a. You can look at the above questions to see the continuity at an x value. If any point which has the continuity meets those three definitions. Let's look at a point here when x equals 2. The function is continuous at x equals 2. Let's look at f of 2 is defined. F of 2 is 3. And limit f of x when x approaches 2 exists. Look at the left-hand limit equals the right-hand limit. Therefore, the limit exists. The third one also can be met. The function value is equal to the limit value. at x equals 2. Therefore, this function must be continuous at x equals 2. I hope that you guys can keep those three conditions for the continuity of a function at an x value firmly in your mind, especially to HL students. HL students need to apply this definition with those three conditions to prove why a function is continuous at x equals a value a in the optional calculus. Right now, let's look at section 4, rules for limits. Here, you can see 5 rules for limits. And I hope HL students can get more familiar with those rules for limits than SL students, because HL students need to know how to apply those rules for evaluating more complex limits in the optional topic. Rules for limits. If there are two functions, f of x and g of x, such that limit f of x and the limit g of x, both of the limits exist when x approaches a, and c is a constant, then the limit of a constant is a constant. The limit of c times a function, you can take the c out, equals c times the limit of this function. The limit of the sum and the difference of two functions equals the sum and the difference of the limits of these two functions. The limit of the product of two functions equals the product of the limits of these two functions. The limit of a quotient of two functions equals the quotient of the limits of two functions. Of course, for the quotient, you need to understand that the denominator limit cannot be 0. This limit, g of x, cannot be 0. As to these 5 rules, you are not expected to know how to prove them, because we will never learn the abstract definition for limits in our DP math courses. We usually use the abstract definition to prove those 5 operation rules for limits. Section 5, evaluating basic limits. Usually we can use those 5 techniques when evaluating basic limits. To be honest, you also can use those 5 techniques to evaluate more complex limits. The first technique is called sub-in. What does that one mean? We will use an example to show you the technique of sub-in. Factoring and simplifying. You can see these 2 techniques can be applied to a rational function. So you factor the top and the bottom and reduce the function to the lowest term. Use a graph or table values. So if sub-in doesn't work, if factoring and simplifying don't work, we can use a graph or table values to look at the limit of a function when x approach a. Dividing by the highest power of x when x approaches positive infinity or negative infinity, we will focus on this technique in the next lesson, 14b for SL, 17b for HL students. Multiplying by the conjugate. But this technique won't be introduced in SL level. Only HL students need to work on this one. HL students will be working on this technique in the optional calculus. Before we evaluate the limits, we also need to know some important things. The first one we need to know is determine the limit forms. We look at the form of the representation of a function. We can predict whether this limit can be determined or not determined directly. If you can see a function is in the form, for example, c over x. So I'm looking for the limit value of c over x when x approaches 0. When you use sub-in, so we use 0 to replace x. So this one is called a c over 0 form. c over 0 is called a determinant form. Why? Think about this limit. You can use a graph or table of values to help you get the idea. C over x, if c is positive, the graph should look like this one. When x approaches 0 from the left-hand side, y value is approaching negative infinity. When x is approaching 0 from the right-hand side, your y value, look at this part, this piece, is approaching positive infinity. You also can use the number sense to help you understand this one. Think about x is approaching 0 means you have a constant divided by a number which is getting closer to 0. So c, any constant, divided by a very small number value. Don't you think the entire fraction is either going to negative infinity or positive infinity? Some of the students may want to ask, how did you know you can graph c over x, this function, when c is greater than 0 in this way? I hope that you guys have very good cumulative knowledge from chapter 1. We learned c over x, y equals c over x, y equals 1 over x in unit 2. Go over the rational functions in chapter 2 again. Okay, you will refresh your mind. Okay, so let's look at c over x when x is approaching infinity. So when you sub infinity in for x, let's still assume c is greater than 0. When x is approaching positive infinity, you look at the function value, y is approaching 0. When x is approaching negative infinity, the y value is also approaching 0. Anyways, c over infinity is a determinant form. When x is approaching infinity, c over x is approaching 0. You also can use the number sense to help you understand that one. So x can be a positive large number or negative, very negative number. Anyway, c is a constant. A constant divided by 1 million, a constant divided by negative 1 million, a constant divided by 1 trillion, a constant divided by negative 1 trillion. Don't you think this fraction value is approaching 0? 0 over c, the function, could be taken as x over c in the limit. This form is also determined. Look at it. If I sub this 0 in for x, 0 divided by c, 0 divided by any non-zero number is always 0. If you want to graph this one, x over c equals 1 over c times x. This graph should be a straight line. Therefore, when you look at this graph, x is approaching 0 on the left-hand side, y is approaching 0. X is approaching 0 from the right-hand side, y is approaching 0. The last form for the determinant forms is limit x over c when x approaches infinity. So sub infinity in for x, that's called infinity over c form. Infinity, positive infinity or negative infinity. Infinity divided by c. Don't you think it's always infinity? You still can use this straight line to help you understand why this determinant form is infinity. Look at it. When x is approaching positive infinity, y is going to positive infinity. When x is approaching negative infinity, the y is going to negative infinity. If you take c value with a negative value, you still can find a 0 for 0 over c. Infinity for infinity over c as well. Okay, I tried to use the easiest looking function to help you understand all those determined limit forms. Later on, those x in each function also can be replaced with a more complicated looking function. As long as the entire denominator is approaching 0, c divided by the denominator which is approaching 0, this entire fraction can approach positive or negative infinity. When the denominator approaches infinity, positive infinity or negative infinity, the entire fraction approaches 0. When this x goes to the numerator approaches 0, the numerator divided by constant is still approaching 0. So the numerator, which is approaching infinity divided by constant, still approaches infinity. Those forms are called undetermined limit forms. After you sub x equals a into a function, if you can see the function form becomes 0 over 0, infinity over infinity, infinity minus infinity, infinity to the power of 0, 0 to the power of infinity, 1 to the power of infinity. Those forms cannot help you determine the limit value directly. You need to do actual work to determine those limits then. Right now, let's apply the above knowledge in 1 and 2 in this section to help us evaluate the limits algebraically. Let's look at the first one. Find the limit of 2x squared minus 5x plus 4 when x approaches 5. The first technique you need to remember is called subbing. If you sub x equals 5 into this function, you can find the y value. This is a defined value. Your limit value is done. So let's sub in. We use the 5 to replace every single x in the function and calculate this one. This is 50 minus 25, 25 plus 4, 29. You also can use the graph to help you understand why this limit is 29 when x approaches 5. This is a quadratic function. I hope that you should have already known quadratic function is a continuous function at any point, at any x value on its domain. So this is a quadratic function. When x equals 5, you look at it here. So since it's a continuous function, when x is approaching 5 from the left-hand side, the y value is approaching 29. When x is approaching 5 from the right-hand side, the y value is approaching 29 from that side. So the limit value can be found by using subbing right away. What is limit 7 when x approaches 1? Let's go back to the rules for limits. The first one, limit of a constant is equal to this constant. Therefore, limit 7 when x approaches 1 is 7. Can we use the graph to justify my answer? Yes, we can. Y equals 7 is a horizontal line. When x approaches 1 from the left-hand side, y approaches 7. When x approaches 1 from the right-hand side, y still approaches 7. Therefore, the limit of a constant is always the constant itself. Right now, let's look at the next example. How can we evaluate this limit? Limit x over x cubed when x approaches 0. Let's sub in first. If I use 0 to replace the x here and the x in the denominator, I will have 0 over 0. This form is called undetermined form. If you see this form after you sub the x equals a value into the function, this form tells you you need to do actual work in order to find its limit. Which work should I work on? X over x cubed. Don't you think you can simplify this fraction? This simplifying means I can reduce this fraction to the lowest term. Let's reduce it. It's 1 over x squared. Then we sub in again. X equals 0. To replace this x, 1 over 0. What is 1 over 0? Let's look at it here. This is called a determined form. A constant over a denominator which approaches 0. So this one will give me positive infinity or negative infinity. But in this case, we should have positive infinity. Why? Because this one is a positive constant. And when you replace this x with 0, the 0 can be on the left side or the right hand side. But when you square it, x squared must approach 0 positively. Positive divided by positive is positive. And 1 over 0 is infinity, positive infinity. Right now, let's look at D. There is a typo in the denominator. It should not be h squared. It should be h. So delete the square in the denominator. So we actually are looking for the limit of 5h plus h squared over h when h approaches 0. How can we find its limit? The first technique is always to sub in. If we sub h equals 0 in for h, we will have 0 in the numerator, 0 in the denominator. It's 0 over 0 type, 0 over 0 form. That's called undetermined limit form. This form suggests that I need to do actual work in order to find its limit. So the actual work will be, since this is a rational function, so I will use factoring in the numerator, factoring in the denominator if possible. There's nothing you can factor in the denominator. Let's keep h there. But we can factor the numerator by taking out h. So h times bracket 5 plus h, close the bracket. We can also reduce the fraction to the lowest term as the next step. So this is called the technique factoring and simplifying. This technique usually is applied to work on the rational functions. So then I can sub in again. So this is 0 when we sub in, I can have 5 plus 0 over 1, which is 5. So this limit value is defined. The limit value is just 5. The next one is also the last example for evaluating the limits. How can we find this limit? The first step is to sub in. M equals 2, let's sub in. 4 minus 6 plus 2, 0. 2 minus 2, 0. It's 0 over 0 form. This is undetermined limit form. This undetermined limit form suggests that I need to do actual work to find its limits. So since it's a rational function, I need to think about factoring and simplifying in order to find its limits. Can I factor the numerator? Yes, it's m minus 1 times m minus 2. And there's nothing we can do to factor the denominator. Let's keep the denominator. Can we reduce the fraction to the lowest term? Yes, we can. M minus 2, m minus 2. It's the GCF between the numerator and the denominator. We can cancel these two out. So right now we only have m minus 1 as the simplified function for the original function, and m approaches 2. After I simplify the function to m minus 1, then I sub in again. I don't have 0 over 0 form anymore. So 2 minus 1 is 1. And this value is defined and exists. This reason why 1 is the limit value of this function when m approaches 2. Okay, this is the end of the lesson. Try to do those homework to help you practice, especially the techniques for evaluating the limits.